G'day guys, Mr. Bennett here. Today we're going to be looking at radioactive decay, and I've got just an idea of a half-life, so that's the main thing. Okay, so if we were looking at a half-life scenario over here, let's say we start with a certain amount of material, and so it decays something like this, and you could probably draw a line that goes there with that. The half-life of a substance is the time taken for it to reach half of its original time. Okay, so again, if I'm looking at half of that amount again, divided in two, come down there, and whatever that time might be, would be the half-life of that particular substance. All right, so that's what we probably want to work out for different things. Now, obviously, different types of atoms will have different half-lives depending on what they are. All right, so there is a formula for working this out. So N equals N0, and then you do half to the N. So N0 is the original mass, or the original count. It might be mass or count. N is the count after N half-lives, and the little n is the number of half-lives. Right, so just use an example with that. So let's say we had a mass of 64 kilograms. So basically after one half-life that will be 32 kilograms. And N equals 2, that's going to be 16 kilograms. N equals 3 half-lives, that will go down to 8 kilograms. N equals 4, that will be down to 4 kilograms. And N equals 5, that will be 2 kilograms. All right, so if I said to you N, and we started off with 64, and we did that to the power of, say, 4, so in other words 4 half-lives, that's going to be 64, and that's going to be a half. So that will be to the power of 4, and 2 to the power of 4. Probably don't really need to do that. I think you can just do this in your head. So that's going to be 2 to the power of 4 is in fact 16. So 64 times by 1 over 16 is going to give you 4. Okay, and that matches with what we're expecting to do over here. Right, might have the scenario where you were given the original amount and you were looking at that period of time. So let's say if I said to you N is 2, actually I might do some different colour. Right, so N's equal to 2, and we started off with 64, and we've got that to the power of N. We want to work out how many half-lives that is. All right, so then what we can do is go 2 divided by 64. That's equal to a half to the power of N. 2 divided by 64 is going to give us 1 over 32. All right, that's equal to 1 to the N. And then we know we're looking to power 2. So that's going to be 1 over 2 to the power of 5. So we're equating these two things here, and then I can say that's equal to 1 to the power of 5. All right? So then that says, therefore, N's equal to 5. Right, so that's the idea. The other way you can do it is without using a formula, is just to manually do it, okay, each time. So if I said to you, you had 100, and we want to work out the time it takes to get to a certain amount. So the next thing is going to be 50, 25, 12.5, 6.25, 3.125. So therefore, I said to you, how long is it going to take to get down to 3.125? You can go 1 half-life, 2, 3, 4 half-lives. Over there, it's a simple scenario over there, the half-lives. Okay, now, so the half-life is originally the amount of time it takes for it to get to half its original mass or half its original count size. Now, there is a nice PhET simulation over here. It's called radioactive carbon dating or half-lives. So this one we've already seen with the plutonium, right? So if we basically resettle the nuclei, right? So this is the decay of carbon 14 to nitrogen 14. Okay, so going there doesn't show you really all that nice a graph, but this one's probably better. If I resettle the nuclei, you can see the carbon is decaying and therefore the nitrogen's increasing at that particular point. So 1 half-life is roughly about 5,000 years. Okay, 2 half-lives is about 10,000 years. So it's about 5,000 years for the carbon-14 decay. We've got over here, we've got some measurements. This one's quite interesting. So if we looking at that, I'll just reset that so you can see the idea of this. So this is looking at carbon dating. So we're planting a tree, right? So the tree is growing, and after a certain number of years, that tree's died. Okay, and now what's happened here is there's a certain amount of carbon-14, carbon-12, carbon-14, and what we're looking at, radiocarbon dating, is related to the ratio of carbon-12 to carbon-14. All right, so therefore, if we know that ratio, we can actually work out how many half-lives carbon-14's gone through, and then we can work out how old the tree is. There's also another little activity you might want to have a go at. It's called the carbon dating game, and you can have a guess. So it tells you what it is, percentage. So it's worthwhile having a go at there. Right? It's a nice little PhET simulation here for you to have a go at. So the other activity I'd like you to do is to actually do the cube simulation over here. So we've got the number of rolls. So we're going to start with 100 cubes initially. So all you have to do is open up the spreadsheet and type in. So let's say for the first one we did 10 cubes that came up. The next one we had something like 12 cubes. The next one we had 15 cubes roll over. We had 16 cubes, 8 cubes. So all you're doing is actually putting the number of cubes that you started with. I mean, you're pulling out each time, and then it's working out a half-life. So from here, I'd like you to work out what your half-life is for this particular scenario for the cubes, and I'm going to have a discussion with you regarding that. All right, so hopefully you get the key concept. The key concept for this particular thing is that the half-life of a particular substance is... Now, I hope you get the key idea here. Okay, the key idea that a nuclear decay is a random process. That's the first thing. Right, that the half-life of a particular substance is the time taken for it to get to a half of its original mass or count number. Okay, and we've got a formula here we can use to actually work out the radioactive decay. Or the alternative method is just simply keep halving what you started with until you get down to. Now, if I knew that this half-life for the black one worked out to be 2,000 years, right, in the case of a tree, then that means that this tree here would be 8,000 years old. Okay, it does have to be whole half-lives. It can be, partial half-lives as well. Anyway, hopefully you enjoy actually doing the simulation, and this is a worthwhile video.